The title of the paper presented is Towards Automated Pipelines for Processing Load Test Data on a High-Speed Railway Bridge in Spain using a digital twin. The authors are Mr. Carlos Ramonelli and Rolando Chacon. So I don't know if the presenters are there or they will present it.
I'm here.
Okay, perfect. So please go ahead. You have 15 minutes and then we have some time for questions.
Okay, so good afternoon. My name is Carlos Ramonelli, and today I will be presenting the work we've been doing to establish a pipeline to process data that is generated during a load test of a bridge. That is a high-speed railway bridge in Spain, and we want to embed this pipeline into a digital twin. So these are the contents of the presentations. First, I will go through a brief introduction of the study. Then I will explain the case study. Then I will explain how we implement digital twins in the case study, and then how we build the pipeline using the former parts. And then this study was 1 year ago, so now I will make an update of where we are now. So this study is carried out within the ASHWIN project, that stands for Assistance for Healthy, Safe, and Productive Virtual Construction, Design and Maintenance of Assets using Digital Twins. More specifically, we are working on the development of a toolkit that is called MatchFem, that aims at integrating IoT with numerical analysis to calibrate model to be used in a digital twin. So the project also provides a large number of demonstrators. As you can see, they are spread along all over Europe. And we are only focusing on the first one, that is load tests in bridges. And yeah, now we move to the case study. So we perform load tests in a high-speed railway line that is located in Spain, in between Madrid and Badajoz, that is a city next near the Portuguese border. And this line has 4 bridges that were tested. We are focusing only on one, that is La Plata, that is this bridge here, that starts service in July 2022. So not right now. And yeah, what is a load test, a proof load test? So it is a structural assessment that is carried out in between the construction and the operation phase to prove that the structural performance is as designed, as we wanted. So the load test is has different tests in it that can be static test or dynamic test, and these are required by law. And then we have a standard. It is a standardized process that the Spanish authorities made. And the objective is to match data that we have on the field with the as-designed models that we created before constructing the bridge. And for that, we measure accelerations for the dynamic response, we measure deformations, and also vertical displacements. So after matching this data with the model, we will get a reliable model that can be used in a digital twin to perform numerical analysis in the future. So it is the birth of the digital twin ability to perform a structural analysis. So now we want to do this in a digital twin. So how we build one and what is it? So a digital twin is a virtual replica of a real asset that is actively connected with it. And in this case, the real asset had a series of sensors as information sources from there that send information to the virtual replica that in our case is formed by the compose of an IoT platform that is linked to an information model, and to this tandem we can connect pipelines that add functionality to the digital twin. So yeah, that's a bridge, the real asset. And for the information model, we use IFC, that is a BIM standard. With IFC, we can model geometry, but also semantics related to built entities, resources, and also processes. And it's in these processes where we can model the load test using each test of the load test is an IFC task that is part of an IFC schedule, a work schedule that is the load test, that is part of an IFC work plan, that is the maintenance plan of the bridge. So this model has a lot of interconnected information, and in this figure here, we can see how we connect the load test, the model of the load test, with the model of the bridge. You can see that we connect different tasks to a specific beam on the model, and that beam has also connected sensors, so we can access the data of the sensors through the beam that is connected to a specific task in the load test. And for the IoT platform, we use Mainflux. That is an open source platform that everybody can use. And it's very easy to use, and it connects devices in the field with third-party applications using two entities, mainly, that are things. That things are anything that provides information to the platform or to the applications. And the channels. The channels are the pathways through which the data is running from the devices to the applications. So we need to map these two entities, the information model and the platform. How do we do this? We map the unique identifiers of the IFC sensors with the unique identifiers of the things in the IoT platform, and we map the identifier of the load test or the work schedule with the channel of the IoT platform. Then what we have, and we can say it with natural language, we have a sensor that is sending information through a load test. So this is a quick snapshot of the platform inside. We can see up, we have the thing information with the ID. Then we have some metadata that contains also information in the model, in the IFC model, just as a backup. If something happens with the model, we can quickly back up the model using this information in the metadata. And here we have the channel to which it is connected. So now we have the information model and the IoT platform connected. How do we add functionality that uses the information there? So we built a pipeline. And we propose to use an event-driven microservice architecture that will have two parts. One is the event that is just a message that contains information and that runs through a whole system of microservices. And eventually one microservice will say, okay, this information is for me. I will activate and perform what I have to do. And the microservice is just a container of code that has a specific functionality that also has a networking capability, so we can connect to the web. And this is a schema of the architecture we are using. So we need two services or two microservices. One is the beam manager service that is in charge of managing all the information in the IFC file and also generating the events that we run through a message broker to all the services that are connected to it. So the other service we need is the load test processing service that is in charge of processing the data generated in the load test. So first, the pipeline starts when we load the data into the Mainflux database. And the second, we activate the pipeline. We trigger the event through the beam manager. So the load test processing can consume it. And this is a little bit the phase of the pipeline. The event that contains information for the load test processing service to activate, retrieve data from the database, process it, and store back the results in the database. And here I didn't want to go into the process itself because it's it's trivial, it's well known within the structural engineers. So I just wanted to show some graphs that this is a vertical displacement during static test. This is the vertical displacement during dynamic test when the train passes by. And this is how we process vibrations in the train. So this happened almost 1 year ago. So where are we now? So we are changing a little bit the architecture. The IoT platform and the functionality inside the BIM manager are being merged into a more complex platform that is a common data environment. It's a BIM concept that is rising now. And then we are trying to get rid of the IFC limitations by just taking the ontology that IFC provides and just instance that using graph models. And then we can expand the information model with our own considerations for processes or so. Then this common data environment has an API that allow the services to connect and perform the functionality that we explained before. And also we are developing a user interface through which we can trigger these events and use this functionality that we are adding. And in this user interface, we can play around with the model, we can visualize the sensor that I read, we can see the information in it, we can select one sensor, select one task in which they have participated, then we can retrieve the data, do something with it, and then we can also see the results of the load test that we will see now. Yeah, these are the results of the load test. We have different hypotheses, and yeah, these are the structural results. And the next step is to, okay, we have the results of the model, we have the data processed. Now we want to calibrate the model. And well, that's it. That's my presentation. Thank you very much for listening.
Thank you very much for such a nice presentation, Mr. Carlos Ramonel. I really enjoyed your explanations. Maybe there are questions at the physical audience in Bogota. Any question? If there is no question, I have some. Sorry, there is one question.
All right. Thank you for a great presentation. And I wonder a simple question. So you showed us the UI platform of your works. So is that platform being updated on real time, or is it something else?
The platform allows us to send information in real time. I don't know if that's a question. Yeah, we can. It's like the platform allows us to connect devices and send information in real time, and we can also upload information data anytime. It has an. Well, yeah, here we cannot see, but it has an API that we can use and send information there.
That was.
Any other questions in the physical audience?
Do you use the IFC ontology only to model all your data model, or do you use a linked data approach where you use various ontologies that you link together?
At the moment, we only use IFC, but we made acquaintance of the limitation it has. So we are trying to change the format so we can extend it. And that's where we are now.
Okay. I'm on the Cogito project, so I see a lot of similarities. So it's really interesting.
Yeah.
Very interesting questions. Any other question? Okay, if there is any other questions, I have one myself. So let's say that the beam has a perfect geometry, and during execution of the bridge, there might be some sort of deviations that need to be considered while placing the sensors, I guess. So is the beams geometry, the one which is in the computer and initial design, considered as ideal, or there is an ideal? Is there another extra measurement of the executed bridge before placing the sensors?
Yeah, this model of this bridge for this application is ideal. It's just the model as designed. Then we are, as the load test processing service, we are developing other tools that use point clouds to fix the differences in geometry that we find in the model and to fix that. But that will be another functionality that can be added to this same architecture. We can connect that in the same way than we did with the load test processing, but another microservice with another code, another functionality, and so.
Okay, and I have another question. How do you measure the loads that are applied onto the bridge?
Yeah, these are, well, I'm going back to the photo I have here. Yeah, so the trains are, let's say, standard as well. So we can, if we know the model of the train that we're using, we know the load, more or less. But we cannot measure that on the field because it's quite complex, because the trains are on rails, and just to put sensor on rails, I don't know if someone has done it, but for load, but we haven't done that yet. The load is supposed load, but I think it's quite accurate because the model of the train is known.
And the speed of the train is also measured, I guess.
Yeah, this is defined. Yeah, this is defined in the standard of the load test. The train passes at 40 kilometers per hour, 80 kilometers per hour, and maximum speed. There are 3 passes, and we measure the information there.
So thank you very much for this, I think, very necessary research, because I guess for the future maintenance of all bridges, this type of studies are necessary to check the loads and to check the movements of the bridge, how much is moving, especially vertically, and if there is maybe even the risk of generating some cracks or damages due to this. So thank you very much, Mr. Carlos Carbonell, for this very nice presentation. We will move now to the next presenter,